Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. Today we are going to start new topic known as Fourier Series. So we will discuss in this lecture some terminology required for this topic known as Fourier Series. So first we start with periodic function. So we define what is periodic function. A function fx is called periodic if there exists a number p which is positive such that f of x plus p equal to fx for all x, and this number p is called the period of fx. So this means suppose we have some function fx and suppose graph of function fx in some interval of length p is like this. Suppose this is the graph of fx in the interval of length p. Now if fx is periodic, then we must have f of x plus p equal to fx. So if we consider another interval of length p, then graph will be repeated in the another interval of length p. So periodic function means there exists a number p greater than 0 such that the graph of function is same in every interval of length p. Suppose I consider interval from minus p to 0, then in this interval also graph of the function will be same. So if there exists a positive real number p such that graph of function is same in every interval of length p, then fx is known as periodic function. And this is the mathematical definition. If f of x plus p equal to fx for all x, then function is called periodic, and this number p is called period of fx. So as I discuss, the graph of periodic function of period p can be obtained by periodic repetition of its graph in any interval of length p. So that means if we have some periodic function of period p, and if we know the graph of function in any interval of length p, then the graph of function will be same in every interval of length p. So this is another example of periodic function. Here we can see, if we consider this interval, length of this interval is 1. So we can see graph of function is same in every interval of length 1. Length of this interval is 2 minus 1, which is 1. So this interval has also length 1, and graph of function is same in this interval also. Similarly, we can see graph of function is same in the interval from 2 to 3, which is also interval of length 1. So this function is periodic function of period p equal to 1. Here we have f of x plus 1 equal to f of x for all x. So this graph represents a periodic function of period p equal to 1. We are familiar with some standard periodic functions. We know that sine of x plus 2 pi equal to sine x, because 2 pi plus x means we are in the first quadrant, and in first quadrant sine is positive. So sine of 2 pi plus x equal to sine x for all x. Therefore sine x is periodic function of period 2 pi. Similarly, cos of x plus 2 pi is also cos x for all x. So therefore sine and cosine are periodic functions of period p equal to 2 pi. And geometrically, graph of sine function will be same in every interval of length 2 pi. Now if P is a period of function fx, then if we find out f of x plus 2p, then we can rewrite 2p as p plus p, that is f of x plus p plus p. Now period of fx is p, therefore f of x plus p plus p equal to f of x plus p. And again, because f is periodic function of period p, f of x plus p equal to fx for all x. That means f of x plus 2p is also equal to f of x for all x. So 2p is also a period of fx. Similarly, we can show that f of x plus 3p is also equal to fx for all x. Therefore, 3 times p is also a period of fx. So in general, if p is a period of fx, then if we consider any integer multiple of p, n belongs to z, so n into p is also a period of fx. If p is a period of fx, then integral multiple of p, that is n into p, is also a period of fx. So in general, if p is period of fx, then f of x plus np equal to fx for all x for any integer n. Therefore, if p is a period of fx, n into p, where n is any integer, is also a period of fx. So we can have infinite number of values for the period of given function fx. Now if among those possible periods, if there exists smallest possible value of period, then that smallest value is known as the fundamental period of fx. For example, we know that period of sin x is 2 pi, and as we discussed, if we multiply 2 pi with 2, we obtain 4 pi. Then if we multiply with 3, we obtain 6 pi, and so on. So all these are multiples of 2 pi. All integer multiples of 2 pi are periods of sin x. So among all these periods, 2 pi is the smallest value of the period. So therefore fundamental period of function sin x is p equal to 2 pi. So if a periodic function fx has a smallest period p, then that period is called fundamental period of fx. So 2 pi is fundamental period of sin x as well as cos x. And a function without fundamental period is constant function, because suppose we consider fx equal to alpha for all x, then we can say that for any positive real number p, f of x plus p equal to also alpha, because value of function is constant at every point. So we have f of x plus p equal to alpha for all x. So every positive real number p is a period of constant function fx equal to alpha, and we know that this is not possible to find out the smallest positive real number. Therefore constant function is the periodic function without fundamental period. So before going for Fourier series, we must be familiar about periodic function. So periodic function is a function for which there exists a number p which is positive real number, such that this condition is satisfied, f of x plus p equal to fx for all x, or the graph of function is same in any interval of length p. We consider some other remarks also which are required for this topic. We are already familiar with this type of values, but we just recall. If we consider this xy plane, then we know that in the first quadrant all the trigonometric functions are positive. In second quadrant only sine function is positive. In third quadrant only tan function, not only tan and cot both are positive. In second quadrant sine and cosec are positive, and in fourth quadrant cos and sec functions are positive. Now if we consider value of sine function at n pi, and if n is integer then sin n pi is always 0. So we will remember all these identities. Sin n pi equal to 0 if n is integer. Cos n pi equal to minus 1 raised to n if n is integer. So cos n pi equal to minus 1 to the power n if n is integer. For example, if we want to find out cos 5 pi, we will consider minus 1 raised to 5, which is minus 1, and cos 8 pi is minus 1 raised to 8, which is 1. Now cos n pi by 2. So if this n is odd integer, then cos n pi by 2 is always 0. That means value of cos function at all these points, pi by 2, 5 pi by 2, 9 pi by 2, 3 pi by 2, 7 pi by 2, and so on. At all these odd multiples of pi by 2, cos function is always 0. Cos pi by 2, cos 3 pi by 2, cos 5 pi by 2. So if we have odd multiple of pi by 2, then cosine function is always 0. Now suppose we consider these values of theta equal to pi by 2, 5 pi by 2, 9 pi by 2. So we can see here there is a difference of 4. 5 pi by 2 minus pi by 2, or we can say that if we consider 1 plus 4, we have 5 pi by 2. 5, if we add 4 to 5, we have 9 pi by 2. Next will be 9 plus 4, that is 13 pi by 2, and so on. So at all these values of theta, value of sine function is 1. So sine theta is 1 if theta equal to pi by 2, 5 pi by 2, and so on. And if we concentrate here, if we complete this angle, it is 3 pi by 2. Then if we add 4 to this 3, we have 7 pi by 2, then 7 plus 4, 11 pi by 2, and so on. At all these points, value of sine function is minus 1. So we will remember all these things which we will require during this chapter of Fourier series. Another important remark is this formula for integration by parts. Suppose we have two functions of x in the product, then integral of uv with respect to x is given by this formula. First u as it is, v1 means integral of function v. v1 is the integral of v with respect to x, minus derivative of u, that is u dash, and integral of v1, which is nothing but v2. Then alternately positive negative, first sign is positive, second is negative, then positive. So now we take second derivative of u, that is derivative of u dash, and integral of v2, which is denoted by v3. Next term is, here we have positive sign, so here we have negative. Here we have second derivative of u, so here it is third derivative of u, and integral of v3, which is denoted by v4. Now in this formula we will select that function as u whose derivative becomes 0 after some finite number of steps. So we have some natural number n, such that nth derivative of u equal to 0. So we will select that function as u whose derivative becomes 0 after some finite number of steps. So that is important thing, selection of u and v. So select that function as u whose nth derivative is 0 for some n belongs to set of natural numbers. Suppose we consider this integral x square cos nx dx. So here we will consider u equal to x square because third derivative of u will be 0 and we will take v equal to cos nx. Suppose we consider u equal to cos nx, then derivative of u will never become 0 and this process will never stop. Okay, here we are considering derivative of first function and integral of second function, and we are continuing in this direction. So if we consider u as that function whose derivative never vanishes, then we are going in the wrong direction. So we will consider that function as u whose derivative becomes 0 after some finite number of steps. So here we take u equal to x square and v equal to cos nx, and we try to integrate now using integration by parts. So we consider u equal to x square, v equal to cos nx. So first term is u as it is. You can see in the formula, first term is u as it is, integral of function v, which is v1. Here v is cos nx and integral of cos nx is sin nx divided by n minus. So this minus comes from the formula. Now here we will consider derivative of first function in this product. So derivative of x square is 2x, and here in this second bracket we will consider integral of this function sin nx by n. So integral of sin nx is minus cos nx by n, and there is one n here, so we have n square. Now here we have taken negative sign, so now we consider positive sign. Again we do the same procedure, derivative of first bracket, integral of second bracket. So derivative of 2x is 2, integral of this second bracket is integral of cos nx is sin nx by n, and we have already n square, so here we write n cube. Now in the next step we will consider again we have negative sign now because here we have positive sign, minus derivative of first bracket which is 0, so we don't have to worry about integral of second bracket. So here because 0 is in the product, this process ends here and we have this term as the last term of the integral. So in this way we will apply integration by parts. We again recall this function was u, this is v. So here u as it is, integral of v which is v1 minus derivative of u which is u dash, integral of v1 which is v2 plus derivative of u dash which is u double dash, integral of v2 which is v3. So first we consider u as it is, integral of v, then alternately positive negative, and we remember in this way. From the second step we consider derivative of first bracket, integral of second bracket, again derivative of first bracket, integral of second bracket, and we remember that we will consider alternately positive and negative signs. So this is going to be very useful in our topic of Fourier series. So we will remember this formula for integration by parts. Now suppose we have this type of integrals, then here we cannot apply integration by parts, because derivative of any of these two functions will never vanish, or derivative of any of these two functions will never be 0. So whenever we have this type of functions in the product, we have this ready-made formula. If we have e raised to ax cos bx dx, then this is equal to e raised to ax a cos bx plus b sin bx divided by a square plus b square. And suppose we have sine function in the product, then in this formula we interchange sine and cosine, and here we consider negative sign. We just interchange these two functions. We write sine in place of cos and cos in place of sine, and here this positive sign is replaced by negative sign. Other things remains as it is. Now for both these formulas, we must have to assume that a square plus b square is non-zero. So all these things are very useful to understand Fourier series. In the next lecture we will see what is Fourier series, and we will see how to represent given function as a Fourier series. So I hope you like this lecture. Thank you very much.